That's a screencast for topic 1, making measurements. So these are the bullet points that you need to know for your exam. These are the definition taken from IB. This is an experiment done by one of the year 13 students. We were proving Ohm's law. So as you can see, on the y-axis we have amps, on the y-axis we have volts, and we know that this was for a resistor, so the material is an ohmic material, and we know that the graph produced should be a proportional relationship, which means that the line graph must go through the origin 0. And as you can see over here, the student got the results, so he got the proportionality relationship, but it was deviated. Each and every point that he measured was deviated from the original actual value due to a systematic error. So if you were to drag this graph all the way to a certain number, fixed number, so it's as if you're shifting all these points, okay, to meet the actual value and to make the line go through 0, then you will have the correct shape of the graph. So systematic errors affect only the accuracy of the results, but doesn't affect its precision. You can see that the results are precise. We like by experiment, we did produce a graph, a line graph, where all the points are aligned, and that's the case for an ohmic material. It's just that all of the values were shifted off by the same amount each time. Second thing concerning the SI units, we know that we have 7 quantities. So you will be asked in the exam to state the specific unit, that's derived unit, in form of SI unit. For example, for the force, we know that force is equals to mass into acceleration. So the SI unit of mass is kilogram, and the unit for acceleration is meter per second squared. And so we can say that 1 Newton is equal to 1 kilogram meter second minus 2. For power, we know that power is equal to the work divided by the time, and we know that work is equals to force into distance. We keep the time. Alright, so the unit of force is Newton, the unit of distance is meter, the unit of time is second, so it's Newton meter second minus 1. You can also, so this is correct, sometimes the question stops here, and if you'd like to replace the Newton, you can replace it by kilogram meter second minus 2, so kilogram meter second minus 2 and meter second minus 1 over here. So you can join the quantities, add them, and yeah, this shows that 1 watts is equal to 1 kilogram meter squared second minus 3, or you can say that 1 watts is equals to Newton meter second per second. Now for adding vectors or subtracting them, the rule is always head to tail. So if you are given this vector x and this vector y, and you're asked to find x plus y, okay, so it's as if you're dragging this vector and this vector and placing the head of the first vector on the tail of the second vector, so head to tail. And then by just tracing, yes, so that's the vector resultant, it's x plus y. For x minus y now, so once again, x, we can drag it as it is, Okay, now for y, if this is plus y, then minus y would be, okay, and just make sure that it's the same size. Yeah, so this is minus y then. Okay, I'll place the tail of this vector on the head of this vector. Okay, yeah. And now the resultant will be by just joining the head and the tail, and this gives you x minus y. In order to be able to do estimations, you have to know the order of magnitude of these quantities. The question will be, let's say, find the ratio of mass of proton to the mass of an electron. So you should know that the mass of a proton is 10 negative 27, and that the mass of an electron is 10 negative 31. Divide them together, and you get 10 to the power of the order of magnitude. It will give you 4. Okay, and that's the answer. Alright, now we look over graph plotting, gradient from a graph, inversely proportional and directly proportional relationships, and how to linearize a graph. Alright, so as you can see over here, these are the different type of graphs that we can get. If the graph is not linear, like this one for example, so it's a curve, but we know that the relationship is y is proportional to x over 2. So instead of representing x on the x-axis, you can replace it by x2, and you can have a linear relationship, which makes it easier for us to get gradient and to analyze. Alright, and that's the whole point of linearization. We're trying to take the curve, change the x-axis or the y-axis, the quantities, and produce a linear proportional relationship. Okay, now you will be asked to explain how the graph verifies a proportional relationship. When they say explain, mean that you need to use words. So you just need to say that it's a straight line, it goes through the origin, and it passes through all the error bars. However, if they ask you to use data from the graph to show a proportional relationship, then you have to pick on your graph, let's say we're dealing with the same one, this one. So you have to pick two points, okay, x1, y1, and x2, y2, and you have to prove that y1 over x1 is equals to y2 over x2, and it's equals to a constant. So if they ask you to use data from graph to show that it's not a proportional relationship, you just need to find the ratio between y and x and prove that it's different, it's not equal to a constant, hence it's not a proportional relationship. And if they ask you to prove an inversely proportional relationship, you also pick 2 points on your graph, and you'll show that, so if they are inversely proportional, then the product of y1 x1 should be equal to the product of y2 x2. It produces a constant value. If not, then the product wouldn't be the same. For gradient, we know that the equation of a line graph is y is equal to mx plus c, where m is the rise over the run. That's the gradient. And what you have to do is to check your axes and replace y and x by the axis, the label of the axis given to you in the graph. So in this case, y is equals to v2 and x is equals to n. Alright, so you find the gradient because you'll have given values, and then you say, since we know that it's a line graph that should have an equation of y equals mx plus c, then in this case it would be v2 equals to k, which is the gradient after you found it, times n. And so if you want to find the relationship between V and N, you can simply square root all the quantity and you will get that V is proportional to the square root of N multiplied by a constant K, which represents the gradient. For uncertainties, there are some things that you need to understand. Number one is that the absolute uncertainty is written as the triangle delta and the quantity is next to it. The absolute uncertainty is the one we draw on graphs as error bars, and it has a unit. Fractional uncertainty is the uncertainty of y over y, so it gives the ratio between the absolute uncertainty and the value itself on one specific point of this graph. Percentage uncertainty now is delta y over y, so the uncertainty of y over y times 100, which means that it's actually just the fractional, but as a percentage. It also doesn't have any unit. Usually in lab, we take 3 measurements of the same value for more accurate results, correct? This is what we're used to do. So to find the uncertainty, we need to subtract the highest value that we recorded from the lowest value that we recorded, and then we divide that by 2. This will give us then the absolute uncertainty. Okay? For example, if the extension of a spring recorded when you apply a force of 2 Newton shows 3 trials. So you have the spring and you attach 2 Newton weight to it. You have over here a ruler and you're measuring the extension, and you recorded this extension for 2 Newton 3 times. So in order to find the uncertainty of this measurement, you have to take the highest value recorded, which in this case is 1.33, and the lowest one recorded, which is 1.19, subtract them, divided by 2, and that's the uncertainty of the extension. But this is only used when we are doing a lab. In exams, you're not asked to find the uncertainty this way. In exams, in most cases, the uncertainty of the 3 measurements and their mean is already given to you as values. And they just ask us to find the uncertainty of an operation. So if it's plus or minus, then you have to add the uncertainty. If it's multiplication or division, this is the rule that we apply. And lastly, if it's an exponent, then we use this rule. Let's give an example for each one. So if we have an extension of a spring 1 is 1.6 plus minus 0.03. Okay, so as I said, they will already give you the mean of the values and the uncertainty, the absolute one, and they will ask you to find, let's say here we have two springs. I want to find the difference in extension between them, and this difference I'm gonna call it Z. Okay, so number 1, you have to do the operation. Since we want the difference, then you just subtract 2.1 from 1.6. You get 0.5. This is the value of Z. Now, what's the uncertainty of Z? You have to just add the uncertainty of extension 1 and uncertainty of extension 2. Okay, if they ask you now to find the constant K of spring 1 when 3 Newton force is applied to it, and I gave you the uncertainty of the force. So the force, the value, and its uncertainty are given. And for spring 1, the extension and its uncertainty are given. You just need to find the constant K. So we know that F is equals to K times E. That's because force is equals to the constant spring multiplied by the extension. To find K, we divide the force by the extension. So as a math operation, we just do 3 divided by 1.6, and that will give you 1.875. Now, in order to find the uncertainty of K, you have to use the fractional uncertainty as per the formula that we stated earlier. So the uncertainty of K divided by K is equals to the uncertainty of the force divided by the force. itself, and plus the uncertainty of the extension divided by the value of the extension. Okay, so it's 1 divided by 3 plus 0.03 divided by 1.6, and this will give you 0.34. Then you multiply by k, which is what we found one earlier, 1.875, and you get 0.65, and so you can say that k is equals to 1.8 plus minus 0.7, and as I said, it has a unit, so the unit here would be Newton per centimeter. Alright, these are some examples. So knowing that speed is equal to distance divided by time, you can find the value of speed, and then they will ask you what's the absolute uncertainty of the speed, or sometimes they don't mention the word absolute. So sometimes they just say, what's the uncertainty of speed? This is the formula. You get 0.09567. Don't round yet. This is the fractional uncertainty, as you can see. If, let's say, they asked you to find the percentage, then it would be 9.6%. But here they're asking for uncertainty, so we have to carry on. We have to multiply the fractional, the like 0.09567 by the value of speed which we found, which is 21.21. And you get 2.029. That's of course meter per second. So the speed with its uncertainty would be 21 plus minus 2 meter per second. Second example, if they ask you to calculate the uncertainty of the speed of 0.4 at 0.4, the distance is, that was the question from the paper, past paper, the toy paper question. Okay, so I'm just showing you that sometimes they will give you, like over here, they gave you the distance and the uncertainty and the time and the uncertainty. What if they gave you, so they gave you the speed, distance and the uncertainty of the distance, but instead of giving you the time, like here, time and its uncertainty, they gave it to you as a percentage. Okay, we will still start from the same rule, and we have the uncertainty of the distance and the actual value of the distance. So what is then delta t over t? It's actually, as we said over here, we have reached the fractional, and you multiply it by 100 to get the percentage. So if the percentage is given, just divide it by 100, you get the fractional, which is this. So you can just say 0.05, and then you'll get 0.063. If you multiply this by the speed, which is given 0.4, you will get 0.025. That's the uncertainty of the speed, 3 times. Okay. Find the uncertainty in the measurement of the length of each pin. So you say the uncertainty of the first pin is equals to max minus min over 2. The max value is 1.60 minus 1.52 over 2. That's 0.04 millimeter. Again, these type of questions are not asked in exams. This is just used in labs. The uncertainty of length 2, this should be 2, this should be 2, is equal to same thing. You just use the second recorded values. Okay, now find the difference in their lengths with their uncertainty. So first you find the average of the length, the average of the second length, and you find the difference. Then you add the uncertainty, because uncertainty is always added, and you get the difference with the uncertainty. Last question, it's something very, very, very important. If we have a cylinder that has a radius of 3 centimeter plus minus 0.3 and a height of 4 centimeter plus minus 0.5, you're asked to find the volume and the uncertainty. So we know that volume is equals to pi r squared h, so 3.14 times 3 to the power of 2 times 4. So far we're just calculating the volume normally. Now for the uncertainty, you say that the uncertainty of V over V is equals to, since this is to the power of 2, we have to apply the third rule, this rule, if you remember. Yeah? Okay, so 2 times the uncertainty of R divided by R plus uncertainty of H divided by H. And you substitute the values, you'll get 36.72. You should round it always to 1 significant figures. So absolute uncertainty should always be rounded to 1 significant. Fractional and percentage, they don't have to. And this is the answer for the volume with its uncertainty. It's a large uncertainty. Now you should learn how to draw uncertainty on a graph, how to count the uncertainty, and how to find the gradient of a line and its uncertainty. Let's start with the first thing. Alright, let's take the first example. So the uncertainty in the measurement of R at each excess temperature is 10%. They gave us the percentage, the fractional percentage uncertainty. We need to draw error bars to represent the uncertainties in R. Remember that error bars are represented by only the absolute. Okay? First, let's find R at 20 and 80. So in order to find that, you have to count how many units we have between the first 2 values. I have 10 boxes. So you do 0.04 divided by 10. That will give you 0.004. So each one small box is 0.004. Okay? If this is 0.4 and we have 20 degree is here, so that would be 0.044. Correct? Okay. For 80, it's approximately here. So if this is 0.16, then that's 0.18, 0.184, 0.188. So approximately 0.88, 188. All right, now, so we have R for each temperature, for each theta. We need to find the uncertainty of each value. So we know that the general rule is the uncertainty of R divided by R is given to us as 10%. So it's given to us times 100, correct? Which means that the uncertainty of R over R in each value is going to be equals to 0.1. For 20, the uncertainty of R at 20 is equals to 0.1 multiplied, because you will multiply by the value of R. So here it's multiplied by 0.044, and that's 0.0044, which approximately gives you 1 box. So from the point, you have to go 1 box up and 1 box down. That's the uncertainty. For R at 80, so the uncertainty of R at point 80 is equals to, once again, it's 0.1 multiplied by R at 80. So we found it as 0.188, and that's equals to 0.0188. Okay? In order to know how many boxes you have to go up and down, you can divide this by the value of 1 box. So approximately 4.7 boxes. Okay, so this is already 0.25 approximately. Okay, as you can see that it's in the middle of the box, so that's 0.25. Then you jump 1, 2, 3, 4 and a half. Okay, so I have half here and 0.25 here. Together they give you 75, and in between I have 1, 2, 3, 4. So 4.75 boxes. You'll jump the same amount downward. So This is 4.7 boxes approximately, and that's approximately 4.7 boxes, and that's it. So this is when you have the percentage, fractional percentage given. But sometimes instead of that, they make your life easier and they give the uncertainty directly. So let's see an example. All right, so this is one of the examples that we've done already. We know that the uncertainty at point n equals to 6 and the speed is equals to plus minus 0.025. And this is the working out if you don't remember how we did it. All right, so over here, I'll first draw the error bar at n equals to 6 for the velocity. And then I want to prove how we found this. Okay, so let's start first by the error bar. So this is n equals to 6. I want to know, I want to go up and down by how much? Okay, so it's 0.025. But how many boxes will be 0.025 equals to? So between 0 and 5, we have 1, 2, 3, 4, 5 boxes. So each box is going to be equals to 0.01. Or in other words, half of 0.05 is 0.025. Okay, so from this point, I'm going to go halfway up and halfway down. Okay, so yeah, divide by 2 here, and it's right there. Okay, so at n equals 6, it's plus 0.025 or it's minus 0.025. Okay, now we know that, as I said, we have 5 division, 0.05, so each box is 0.01, which means that the uncertainty here is 0.01, correct? Plus 0.01, and that is minus 0.01. How did we find this? Yeah, that's the formula, correct? And the distance, they said that the distance is fixed. It's 0.75, and uncertainty is 0.01. As I said, since here the uncertainty of time is given to us as percentage fractional, so in order to go from percentage fractional to fractional, because this looks like fractional to me, of course, so you just need to divide what is given by 100, and you get, so it's 0.063. Okay, so to find the uncertainty at this point specifically, we have to multiply 0.063 by how much? How much is this value? 0.18. And this will give you 0.01. And as you can see over here, we have 0.01 up, 0.01 down, just like this. All right, I'm not gonna solve all this question, but it's a very important and it's a beautiful question because it contains almost all the things that we took. Okay, I'm just gonna take this graph and this graph in order to answer the question using the graph on page 2, calculate the percentage uncertainty in D2 of the ring n equals to 7. Is use the graph to determine the value of the constant as well as its uncertainty. All right, so this is the example. We have the graph D versus n, and we have the linear version of the graph. It's D2 versus n. All right, we need to use the graph in order to calculate the percentage uncertainty in D2 of the ring n equals to 7. Now, they told you already to use this graph, okay? Why? Because we need to find the uncertainty of D2. So, uncertainty of D2 over D2 is equals to 2 times the uncertainty of D divided by D. And in order to find the uncertainty of D, we need to use the error bars. And to find D, we need to go to n equals to 7. So that's n equals to 7. and this is the point that we need to check its uncertainty and the value d. All right, so for n equals to 7, let's see this is equals to what? Here we have 0 to 0.02, we have 5 divisions, so each box is 0.04. Okay, how do we do it? Remember, we do 0.2 divided by how many boxes we have, so divided by 5, and it gives you 0.04. Okay, so this is 1.2, that's 1.24, 1.24 approximately. Okay, so we just found D. Now for the uncertainty of D, we need to count how many boxes we have, multiply this by one single box, which is 0.04. Okay, so I can tell that over here we have approximately 2 boxes. Okay, so the uncertainty is going to be equals to 0.08. All right, so 2 multiplied by the uncertainty, which is 0.08, divided by the value of D at n equals 7, which is 1.24, and this will give you 1.29, which is approximately equals to 0.129, approximately equals to 0.13. So this is the fractional uncertainty. In order to find the percentage, we just need to time this by 100, and it gives you approximately 13%. All right, for the second question, what we know is that this is a line graph, so it must have the equation y is equals to mx plus c. All right, so if you draw the line of best fit, if you like extend the line, you can see that it goes through 0, which means that c is equals to 0. So y is equals to mx. Your y is d2, so d2 is equals to m is the gradient. I'm just gonna keep it as m, or they called it k in the question, so let me call it k as well. And x is equals to n. Okay, now we need to find what k is. All right, in order to find k, you need to do rise over run. All right, now how can we find the uncertainty of k? In order to find the uncertainty of k, we need to find the worst fit, the maximum worst fit and the minimum worst fit. The maximum worst fit you can take, so you take the head of the first error bar with the tail of the last error bar, and you make a line out of it like this. Okay, and the second worst fit would be the tail of the first error bar with the head of the last error bar, just like that. All right, now what you have to do is you need to find k max and k min. All right, and you do this by choosing 2 points on each line graph. You need to make sure that they're as further away from each other as possible. Okay, so for your k max, and that gives you 0.25, approximately 0.19. Now to find the uncertainty of k, you have to say 0.25 minus 0.19 over 2, 0.03. So we can say that k is equals to 0.23 plus minus 0.03. And the following question, they said, what is the unit of k? So k here is equals to d2 divided by n. N has no unit, as you can see over here, so it's unitless. And d2 has unit of centimeter squared, so k will also have the same unit as d, so it's centimeter squared.